Hi, this is Elias Fofanov, aka Engineer Spock from engineerspock.com, and in this section we're going to learn one of the most important principles of object-oriented design, the Dependency Inversion Principle, or DIP in short. Here is the outline of this section. First, we will start from the definition of the Dependency Inversion Principle, as usual. The definition will lead us to the necessity of understanding what is a dependency and what types of dependencies exist. Dependencies will lead us to the notions of inversion of control and dependency injection. You'll see the problems caused by DIP violation. The analysis of the problem will bring us to possible refactoring techniques which allow us to fix the problems related to the DIP violation. You'll see the refactoring process which helps to adhere to the DIP. You'll see the architectural implications of adhering to the DIP. You'll learn what IOC containers are and how to build a simple one on your own. Separately, I'll show you a non-trivial example of building an application with an IOC container. Of course, we will look at common smells of DIP violation. And in the end, we will draw a conclusion. In the next lecture, we will define the DIP. Let's get started. This lecture is titled Definition of DIP. The Dependency Inversion Principle is all about decoupling. This is very important, so I'll remind you what coupling is. Coupling indicates how dependent modules are on the inner workings of each other. Tightly coupled modules rely extensively on the specific state of each other, sharing variables and many types. Loosely coupled modules are fairly independent. They have a few well-defined APIs and share a limited amount of or no data at all. So decoupling is what we strive to. It is the process of achieving loosely coupled modules. You can understand modules here both as classes or assemblies. The DIP is applicable at different levels, at the source code level and the binary level. If you look at Wikipedia, you'll see that low coupling is often a sign of a well-structured computer system and a good design, and when combined with high cohesion, supports the general goals of high readability and maintainability. Well said indeed. So, what is the formal definition? According to the Agile Principles, Patterns and Practices in C# by Uncle Bob, high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. Seems like this is a definition with two levels. The first level concerns modules and the second concerns abstractions. This is a great definition, however, as always, it requires some further clarification since it's very hard to apply and practice such advices without seeing any practical examples. I want to show you a picture which demonstrates the DIP in real life. Given a lamp, socket, and a solder, a question arises. Would you solder a lamp directly to the electrical wiring in a wall? If you do that, you'd be able only to use that socket for that lamp, because they are, so to speak, tightly coupled. To fix the problem, we need to come out with a standard plug, which you can see on the right small picture. If all the devices implement such a plug, then they can be plugged into the socket. The same is true for dependencies in code. The high-level policies should not directly depend on low-level details. In case of our picture, devices are not directly depend on sockets. You can find an exception from almost all the rules, so look at this picture. This is a cheap hotel where the hair dryer is wired to the socket directly. But in this case, this is done intentionally, and actually it is meaningful. The intention in this case is to defend the dryer from thieves. Again, this is a rare case. In this lecture, we mentioned the notion of a dependency. In the next lecture, we will look at dependencies more closely. This lecture is titled Dependencies. Let's define what we mean by a dependency. There are several types of dependencies: framework, third-party libraries, external systems like file system, database, or any system resource, and so on. Dependency on a custom type built on top of the .NET framework. In this section, the most important type of dependencies for us is the dependencies on custom types, which are developed by us. For example, here on the slide, the person class depends on person repository class. Person cannot provide its features without relying on the person repository class. The person repository is a low-level class which interoperates with a database, while the person is the high-level domain object. So, in this particular case, a high-level object depends on a low-level object. Such a case is aligned with how beginners build software traditionally. This is a high-level view on a classic application with 3 tiers, or 3 layers. On the top, we have a user interface. A user interface calls API of objects which implement business logic. Objects which implement business logic call the API of low-level infrastructural objects which implement interoperation with a database or external web server, and so on. What's wrong with the relationships between layers on this diagram? Do you know what it is? The problem is that high-level objects of the domain layer directly depend on low-level objects of the infrastructural layer. The lamp is soldered to the socket like a vise. What would you do if a requirement to change the database management system comes into play? It's hard as hell to replace a dependency if there is a tight coupling between the dependencies. The most frequently changing parts reside on boundaries of a system. User interface and DB-related stuff are irrelevant from the domain perspective, so the domain logic should be independent of irrelevant things. To fix the problem, we need to revert the dependency which points towards the infrastructural layer. On this example, I'll show how we decouple one abstraction from another. A fundamental theorem of software engineering states that we can solve any problem by introducing an extra level of indirection. So let's do exactly that to decouple person from the repository. Here is the slide which reflects the changes made by a simple refactoring. We often refer to such interfaces as to seams. These seams allow us to inject any dependency we want, which of course implements that interface. This is a simple yet powerful technique to invert the dependencies, achieving low coupling between components. Another interesting aspect concerns runtime and compile time dependencies. Look at the diagram. Here we have a module A that calls function F on module B through an interface. When we use polymorphism, creating an interface, inserting it between module A and module B, we end up with a situation when module A has only a runtime dependency on B, but it doesn't have a compile dependency on it. We can compile just module A if we want to, without recompilation of module B. In languages like C++, it helps to significantly reduce the amount of compilation time. Okay, that were the basics of what the dependencies are. In the next lecture, we will take a closer look at 2 major types of dependencies. This lecture is titled Volatile and Stable Dependencies. In the previous lecture, you saw on a simple example how to invert the dependency on a repository by introducing a layer of indirection. A logical question which comes to mind concerns what dependencies should we abstract away? And to answer this question, the first thing we need to do is to realize that all the dependencies can be divided into two camps, volatile and stable dependencies. Let's define volatile, or in another word, unstable dependencies. According to Mark Simon, a dependency should be considered volatile if any of the following criteria is true. The dependency itself depends on the environment, forcing the caller to set up that environment. A classic example would be a dependency on a database, or any types that imply interoperation with a database. Any other external systems like web servers also fall into this category. The dependency doesn't yet exist and is still under development. This is a regular deal when we want to write code which, among other things, interoperate with an object inexistent at this point. We don't want to wait that object to be written, so we just introduce a SIM which reflects the API of that object and make calls through that SIM. The dependency which is not installed on all machines of developers. And the dependency has a non-deterministic behavior. It can depend on datetime now, random numbers generation, and similar unstable by their nature things. In general, we can define stable dependencies as dependencies that are not volatile. It may sound odd, but it's quite simple and useful, so we will stick with that definition. Volatile dependencies are those which we want to abstract away by introducing levels of indirection. Since they are unstable, we at least need to have a way to replace them by test doubles in unit tests. Otherwise, we may end up with an untestable application. Remember that you can't treat an application testable until its design allows to write unit tests. If an application allows only integration tests, it should be considered untestable. Let's elaborate the topic of DIP by learning very close terms IOC and DI. We will talk about them in the next lecture. This lecture is titled Definitions of IOC and DI. In the lecture where we discussed the notion of dependencies, we saw this diagram. If you look more closely, you will notice that module A has a relationship of composition with the interface. It means that we need to inject the module B as the implementer of that interface somehow. This example demonstrates what is dependency injection. Dependency injection is one of the most important notions we will use throughout this section, so let's separate dependency injection and dependency inversion principle to avoid misunderstanding of these closely related to each other concepts. There is actually another general term, inversion of control, and you also should understand the difference between this term and the previous two we talked about. So let's give definitions to these terms. And we will start from the IOC. Inversion of control is a very general term which reflects the model of relationships between a caller and a callee. A classic flow of control implies that a client has a full control over the environment and sequence of calls to library methods. The inversion of control implies that a callee, we can imply any library methods when we say callee, take the control over some calls between the caller and the callee. The simplest form of inversion of control is callbacks. The main idea of a callback is to provide a way for a callee to call a caller back. So that's why there is a very important difference between regular libraries and frameworks. Frameworks rule the client code. Frameworks provide plugs which have to be just filled by clients. Frameworks also have the control over the environment. This is the inversion of control in action. Dependency inversion principle is a more detailed version of the inversion of control notion. DIP concretizes that high-level modules should not depend on low-level modules, and so on. Inversion of control is a meta-principle in a sense. According to the definition of the dependency injection given by Mark Simon in his book Dependency Injection in .NET, which I recommend to you very much, dependency injection is a set of software design principles and patterns that enable us to develop loosely coupled code. At the same time, you need to understand that IOC can exist without DI. IOC is possible without DI because we can change implementation by relying on subclassing, for example, by applying the template pattern, which was discussed earlier. Nevertheless, the main way to perform the inversion of control is to apply dependency injection techniques. In the next lecture, you'll see an example of DIP violation. Here is a simple demo which demonstrates the essence of a problem. In this case, we have a class named Divergence Checker, and here is what it does. We have two physical devices which are represented by two classes, a counter and fiscal registrator. This is a case from my own practice. In Russia, when we sell anything, we need to register the selling operation in a special device called fiscal registrator. In my case, we have a separate device which performs encrypting and decrypting operations and unfortunately has to double the responsibility of a fiscal registrator, keeping all the details about sales in safety. As a consequence, we need to periodically check that there is no divergence between counters of a fiscal registrator and that special device represented here by the counter class. To perform that check, I implemented this class. Right now, this class logically has two dependencies. It depends on a counter and fiscal registrator. These classes directly talk to physical devices. In real world, this class exposed more than one public method, but in this case it's enough to have the only one to demonstrate the problem. This method actually checks if there is a divergence between counters of two devices. This method uses both dependencies. It takes two counters from one device and logically same counters from another device. Then it just checks if corresponding values are equal. Okay, let's say we want to write a unit test for the hasDivergence method. How are we going to do this? With the current design, there is no way to write a unit test. The GainDivergence Checker class is tightly coupled to a counter and fiscal registrator. These dependencies are unstable or volatile since they represent real physical devices. Physical devices are always inclined to unstable behavior. That's why we can't write trustworthy unit tests in this case right away. Okay, in the next lecture, we will look at 3 ways of applying dependency injection to fix the problem. The root cause of the untestable design in this case is that this class is dishonest. It lies to its clients. It lies about the fact that it has 2 dependencies. It lies by hiding them. The obvious way to fix the problem is to make dependencies visible. There are 3 major ways to accomplish that: constructor injection, property injection, and method injection. Constructor injection is when we request dependencies to be passed via the constructor. So the obvious refactoring can be done as this. The first thing we need to do is to create a seam which will serve as a boundary between domain logic and external devices. And so I move to the fiscal registrator class and go to refactor
extract interface, and I am going to extract all the public members. And here you can see that fiscal registrator now implements iFiscal registrator with two methods, and the same goes with the counter. I extract an interface, selecting all the public members, and ReSharper generates that interface for me. You can see that.
Now we can continue our refactoring process.
And the next part of our refactoring is to request our newly created interfaces in the constructor, like this. So now the client will have to pass an implementation. And we assign our interfaces to the fields.
Now a client can't create the gain divergence checker without thinking of dependencies. A client sees them and has to decide what to pass in. The responsibility is shifted to the client's side, and this is good. Now we can write a unit test replacing these dependencies by test doubles, which are under the full control of a client's code. Before writing a unit test, look at the other two options, property injection and method injection. Firstly, let's look at how code will look like with a property injection.
To implement a property injection, at first I'll comment out our constructor and two fields, and now I'll create two properties. One is for injecting the I counter with public setter, and another one for injecting the iFiscal registrator. And of course now we need to use these properties like that.
The difference between this option and the previous one is that the client's code can reset the dependency whenever it likes. At the same time, from the API perspective, a client now can create the gain divergence checker and forget to set the dependencies. After that, it can call the hasDivergence method and face the null reference exception. It means that the encapsulation of this class is broken. It doesn't provide guarantees that its methods will work as expected. Another option is to request the dependencies in the method where they are needed.
It's quite easy to perform this refactoring as well. I just comment out our properties and request the dependencies in the hasDivergence method.
It may look like a little bit weird, but it is absolutely valid option. In this case, the client's code will be unaware of any dependencies until it calls the method. This design preserves the encapsulation. It provides guarantees that the hasDivergence method works as expected in any cases. Let's write a unit test which validates the correctness of the hasDivergence method.
At first, I want to get back to our constructor injection way of ruling the dependencies. So I uncomment the constructor and our fields and use them in the hasDivergence method. And now I can add a unit test file to the corresponding project. I'll name it gain divergence checker tests. I'll make it public and covered by the test fixture attribute to run the tests from within this class, and write the first method, testing method, which I'll call hasDivergence returns correct result. And I'll create a testable fiscal registrator, inheriting it from iFiscal registrator. And what am I going to do here? I'll define the sales sum decimal and sum of return tickets, reflecting the intention of this class, but I return the value which is going to be set via properties directly, and the same goes with the testable counter. So I even copy and paste all the code, and I'm going to use test cases here, and because of that I add several properties: a counter sales and a counter returned. And of course the same for fiscal registrator for values. And I add test cases. So 100, 100. Yeah, and I'll add another one, expected result, because our method that we're going to test, I'm talking about the has divergence method, returns Boolean. So when all the values are the same, we expect true. The second and third cases are true because sales are equal, and the last two cases are false. Okay, and now we can use our testable accounter and testable fiscal registrator classes. So at first I initialize the testable accounter, passing the values from our cases. And the same goes with fiscal registrator. So I create an instance of testable FR and assign to an interface. Then I create our system under test, which is the gain divergence checker, passing our implementations. I'm passing, or in other words, injecting our implementations into the gain divergence checker constructor. Then I act on it, calling the has divergence, and then assert that expected result equals the actual result. And now we can go to test and open up the Test Explorer window and run our test.
Great! The test passes. In this lecture, you've seen a simple example of applying the dependency injection techniques. They're indeed really simple. In larger examples, the techniques will remain the same. Before continuing, I want to give a summary of the 3DI techniques we just applied in the next lecture.
This lecture is titled Dependency Injection Techniques. Constructor injection implies that dependencies are going to be passed in via constructor. The most beneficial aspect of constructor injection is that it protects the invariance of the object. The object once created will always be in a valid state. However, you should be aware of the following possible pitfalls. In large systems, constructor injection tends to accumulate many dependencies. You may see more than 3 dependencies requested via a constructor. However, this is not the drawback of the constructor injection itself. Most likely, this is a smell of violating the SRP, or single responsibility principle. In case a constructor requires more than 3 or 4 dependencies to be passed in, consider the possibility to extract some of responsibilities into separate classes. Sometimes it happens that several dependencies tend to be passed in together. Here is a code snippet which shows that a view model takes 4 dependencies, and imagine that many other view models take the same dependencies as well. In such cases, it would be wise to create a container object for them and require that container's object to be passed in the constructors. Seems like it has no effect, but it's always a good idea to join objects which go together in many cases. One day you'll want to introduce a custom validation method which is related to all that dependencies or something like that. However, most likely more than 4 parameters is the smell of the SRP or single responsibility principle violation, as I said. So take a closer look at the responsibilities of a class which requires so many dependencies. Another interesting case concerns the, so to speak, non-obligatory dependencies, like a logger. It's a valid solution to expose several constructors, some of which set the default implementations of the dependencies. You can see here an example. In this case, you may replace in the unit tests the iLogger by a dummy test double, which does nothing. While in the production code, clients can just use the default constructor, since in the majority of cases no one cares about the logging mechanisms. Another pitfall you may stumble upon is that such frameworks like the Entity Framework or other object relational mappers may require from objects to have a public default constructor. In such a case, you will be forced to expose a public default constructor. Otherwise, you'll get an exception in the runtime. Of course, you can consider writing a wrapper around such an object which stands very close to a boundary of a system, thus preserving the encapsulation. If a certain dependency is used only in a single method, then consider removing that dependency from the constructor and request it as an argument of that method, which certainly needs it and cannot provide its service without it. In other words, consider to use the method injection. Property injection implies exposing of dependencies via properties with public setters. It allows to replace the dependency during the entire lifetime of the object. The flexibility is the main advantage in this case. However, the drawbacks are so heavy that we should strive to rely on this way of injecting only in case of non-obligatory dependencies, such as loggers. In such cases, there should always be a default implementation of that dependency, and it should be set in a default constructor, or right in the property. You see the example on the slide. This code, by the way, relies on the C#6 feature of property initialization. In any other cases, you should avoid property injection, since it easily can break the encapsulation of a class and make the dependencies hidden. Dependencies exposed as properties are hidden because no one is obliged to remember all the internal details of a class. Method injection is an interesting technique. Dependencies, which are set via properties or constructors, are usually used by many methods throughout the lifetime of the object. However, sometimes an implementation may vary from one call to another call, or if a method is static. For example, the conversion of one currency to another requires an object which gets the rate. A similar example is the iFormat provider, which is required in such methods like double parse. However, think twice before implementing method injection. If you want to pass a dependency directly to a method just because only that method among 20 other methods uses that dependency, then this is a smell of SRP or single responsibility principle violation. Maybe a separate responsibility is hiding inside of that class. By the way, we mentioned SRP, single responsibility principle, several times in this lecture. So it's logical to pay some attention to this very important principle, which is part of the so-called solid principles. And we will definitely spend some time learning about single responsibility principle, and we will do that very soon. But okay, let's get back. Another problem with this approach is that IOC containers, or DI containers, cannot automatically inject the dependencies to methods. IOC containers are tools which help to automate the process of dependency injection, and we will discuss it further in this section. Okay, now you got the idea of dependency injection and three major techniques. These simple techniques have fundamental implications. Of course, in real life, things can be slightly more difficult than we saw in this lecture. The problems appear at the architectural level. Let's talk about architectural implications of the inversion of control and dependency injection in the next lecture.
This lecture is titled Architectural Implications. Inverting dependencies is the means by which we create boundaries between software modules. When we want to create a boundary, we choose which dependencies to invert against the flow of control, so all of them point in the same direction across the boundary. Boundaries like on this slide are the way we create plugins. A plugin is a module that is anonymously called by another module. In other words, the caller has no idea who or what it is calling. In this case, the module A doesn't know it calls the module B. Plugins can be deployed independently, and moreover, they are independently developable. We divide the system by boundaries and then invert the dependencies that cross those boundaries. So plugins define the boundaries of your system. The old model of building software systems with 3 tiers is the data-centric model. In such architectures, the database and its schema is the center of the system. It drives all the other parts of the system. Frankly speaking, this approach is still alive and sometimes could be beneficial, but nowadays we're inclined to treat databases and UI as tools which can be replaced. In data-centric architectures, a significant part of domain logic is going to be implemented at the database side, so it will be implemented in stored procedures with a language like SQL. The major problem with this approach is that data processing related languages like SQL, which are very efficient in processing of tuples, were not designed to implement business logic, at least significant chunks of business logic. Database-related languages are very poor on features which allow to model relationships between domain objects. This is one of the major reasons why the worldwide community of developers shifted to another approach where the database is treated as a low-level detail. And here we reach the point when we continue to analyze the implications of the architecture based on plugins. Here is a diagram where the domain is in the center. When we treat database and UI as tools which are mostly irrelevant, we come up with the idea that the core of any application is the domain logic. Domain logic is the most stable part of the system, since domain policies change relatively rare. For example, the UI part changes far more frequently. Notice that all the dependencies point towards the domain. If you enlarge this diagram, assuming that these big layers are comprised of many objects, you'll get the following diagram. I've got this diagram right from the blog of Mark Seaman. Notice that all the dependencies still point toward the center of an application. If you add the layers to this diagram, you'll end up with the following. This diagram depicts what architectures call onion architecture. There are other similar notions such as hexagonal architecture and ports and adapters architecture. All these terms mean essentially the same, they are all about the same. Ports are those scenes we introduce by extracting interfaces, and adapters are plugins which come from the boundary of a system. In large systems, the graph of dependencies is very large, though you should strive to keep the graph as flatter as you can. Even if you keep the graph flat, you also can face the problem of controlling the lifetime of dependencies. This leads to an interesting question. Who is responsible for keeping the control over the dependencies' instantiation and their lifetime? And the answer is obvious. Any application starts from the main method. Developers often refer to main as not to a physical entry point, but as to an infrastructural point where all the relationships between dependencies should be set up. The idea of setting up all the dependencies in a single place, in main, actually conforms to the single choice principle that was discussed in the OCP section. Main is the single place which knows everything about dependencies and their relationships. It doesn't necessarily mean that all the dependencies will be instantiated in main. Some of them may be instantiated in main indeed. The other will be automatically created in the runtime according to the setup made in the main partition. In this lecture, we figured out that the main is the infrastructural point where we set up all the dependencies. Now we need to understand how to set up them in practice. In the next lecture, we will look more closely at pure DI and IOC containers. They are related to two major techniques which allow to set up the dependencies and inject them properly.
This lecture is titled Common Smells of DIP Violation. All the common smells of DIP violation take their roots from the DIP definition. DIP clearly states that high-level policies should not depend on low-level details. So the common smells are the following. A class explicitly creates one or more dependencies, hiding them from a client. A class uses non-deterministic dependencies like datetime or random. There are ways to decouple such dependencies, which often come from the .NET framework itself. One way is to extract a class which works with non-deterministic dependencies and cover it by integration tests, and another option is to create some kind of adapter. I mean, create your own interface and implement it in a custom class which uses non-deterministic dependencies internally. And then you can use that custom interface in the production code and replace it by test doubles, which are under your control in unit tests. A class uses static dependencies. Very often they are singletons. Singletons make unit testing very difficult. Static dependencies of a class are also hidden from a client. So if a static dependency was not properly instantiated, then a class will most likely behave itself incorrectly, throwing exceptions and so on. This forces clients to remember about hidden dependencies all the time, and this is almost always a bad thing. The main idea of removing the DIP smells is that you need to extract a layer of indirection and make the class which violates the DIP dependent on that layer of indirection. Another principle which often helps is the single responsibility principle. Adhering to the SRP often helps to avoid extracting of useless interfaces. And before moving to the conclusion, I want to spend some time to talk about the SRP, the single responsibility principle. So the next lecture will be dedicated to the SRP. It's time to recap what we learned in this section. So, in this section you learned: what is DIP? DIP implies that high-level policies should not depend on low-level details. You learned that there are two major types of dependencies: stable and unstable or volatile. Unstable dependencies are those to which we want to apply the inversion of control. What inversion of control and dependency injection are, and how these notions are related to the DIP and to each other. You learned about three techniques of dependency injection: constructor injection, which should be used in 95% of cases, and property and method injection. You learned that adhering to the DIP leads to a plugin architecture, which is commonly referred as to the ports and adapters architecture. This led us to a conclusion that there should be a single place which knows everything about application dependencies and their relationships, and this place is main. You also learned that manual dependency injection may become tedious, and that's why IOC containers exist, which helps to simplify dependency injection in difficult cases. You learned how to build a simple IOC container. You saw an example of a real-world application which relies on an IOC container and sets it up in main. We also summarized what the common smells of the DIP violation exist and how to fix them. Okay, that's it for the DIP. In the next section, we're going to dig deeper the topic of IOC containers. Hi, this is Engineer Spock, and we continue to talk about dependency injection. In this section, you'll learn what is the difference between pure DI and IOC containers. You'll see how to build your own trivial IOC container. We're not going to implement any sophisticated features, though it's an interesting undertaking. The notion of dependency injection and IOC containers is related to the so-called service locator design pattern, so you'll learn what is service locator and when and where it's bad to use. Finally, I'll show you a real-world example of using a DI container. By the way, just in case, DI container is the same as IOC container. These notions mean the same. Okay, in the next lecture, we will talk about the difference between pure DI and IOC containers. This lecture is titled Pure DI and IOC containers. Hopefully, now you understand the possible difficulties you may face applying the dependency injection techniques. Basically, there are two ways of dealing with dependency injection. The first one is to manually create all the dependencies and dependencies of the dependencies and inject them explicitly by calling the new operator passing in the constructor all the required dependencies. Mark Seaman referred to this manual approach as to the so-called poor man's DI. In 2014, Mark Seaman retired this term, replacing it by a new term, pure DI. The reason was that poor man's DI sounded slightly derogatory, or at least unattractive, and it also didn't communicate the message that DI without a DI container is, in many cases, better than DI with an IOC container. On the contrary, it sounded like it's not as good. That was a citation from the Mark Seaman's blog post. I'll show you an example of pure DI from a booking application written by Mark Seaman. You can see here in main lots of code. This is a non-trivial example which demonstrates how difficult it can be to set up and track all the dependencies manually by relying on a pure DI. That's why we have full-fledged IOC containers. So the second way of dealing with DI is to rely on an IOC container. So what is an IOC container? IOC container, or a DI container, is a framework which helps to apply dependency injection. This is the main feature of any IOC container. IOC container injects dependencies automatically. Of course, containers provide the ability to set them up by configuring those dependencies. So, when the client's code asks a container to resolve a particular dependency, a container knows how to create that dependency, and it knows how to create the dependencies of that dependency, so it recursively creates all the necessary dependencies until it creates the requested one. On the slide, you can see a diagram of type dependencies. Imagine that we make a call to an IOC container to resolve the main view model. In other words, we want from an IOC container to get an instance of the main view model class. The main view model class depends on the iCustomer interface. It takes this interface in its constructor. So to create the main view model, the IOC container will look further to find out how to resolve the iCustomer interface. The IOC container will find the customer class, which implements the iCustomer interface. So the IOC container will try to create the customer class. In order to create the customer class, the container has to pass to its constructor the iCustomer repository, since the customer class depends on this interface. To resolve the iCustomer repository, the IOC container will continue to dig deeper and find the implementer of that interface. The IOC container will find that the iCustomer repository interface can be resolved by the customer repository class. But to create an instance of the customer repository class, the container needs to resolve the IDB gateway, since the customer repository depends on it. And finally, the IOC container will create the DB gateway. After that, container will create customer repository, then customer, and then the main view model. So this is how IOC containers recursively resolve dependencies. This diagram doesn't show the IOC container itself. If we put here the IOC container class, it will depend on all these types. It has to know about all the dependencies. It is the job of the container, its responsibility. In the next lecture, I want to quickly demonstrate you how to build a naive implementation of a simple IOC container to clarify the basic mechanism of how they work. Let's implement a very simple IOC container. At first, I will define a map between types. This map will contain a one-to-one relationship between dependencies. Here it is. Of course, we need to expose a public method which allows clients to register dependencies. This is a generic method that takes two types and adds them to the map. There is nothing else to explain since everything is obvious so far. Let's create a public method for resolving dependencies. This method is also generic. The T parameter is the type which a client wants to resolve. This method calls another method which will be private and implement all the logic of the container. Here we get the corresponding type from the map. If we didn't find it, we would throw an exception. Notice that we get a type. This is not an instance of an actual type, it is its descriptor. IOC containers use reflection heavily. Without reflection, it's impossible to analyze type dependencies and create them properly. Having a type, we can request its constructors. We implement a very simple IOC container, so for the sake of simplicity, I just get the first constructor of a type. Having a descriptor of a constructor, we can request its parameters. If there are no parameters, or arguments in other words, we just create an instance of a dependency and return it. Otherwise, we need to resolve them recursively, so we need to do the following. This code recursively tries to resolve all the constructor's arguments. In the end, we want to create an instance of a dependency, so we will call the constructor, passing the arguments. Trust me, this is a very simple IOC container, nothing more, nothing less. Let's try to use it. Let's say we want to resolve the main view model I showed you on the diagram in the previous lecture. Before resolving the main view model, we have to set up the IOC container. So we register dependencies one by one. The main view model is mapped to itself. Interfaces are mapped to corresponding implementers. After that, we can resolve the main view model. Great! I'll set a breakpoint and debug the program to make sure that everything works fine. As you can see, we reached the breakpoint, and if I hover my mouse pointer over the main view model instance, I see that it was successfully created. So everything works fine. And that was the essence of any IOC container. And in one of the upcoming lectures, I'll show you an application which is built with an IOC framework to demonstrate you how real-world scenarios may look like. In the previous lecture, you've seen what is IOC container is in essence. Service locator is a pattern which is very similar to modern DI containers, and actually full-fledged DI containers took place from the service locator design pattern. The gist of service locator is that it allows to create object instances without direct use of the new keyword. Instead, we use some kind of a factory method. Sounds like a DI container actually, but soon you'll see the slight but important difference between DI container and service locator. Here is a diagram which reflects the meaning of service locator design pattern. Most often, service locator is implemented as a static class, like in the following code snippet. The intention of service locator is the same as in the case of a DI container, to decouple business objects from their dependencies, separating the responsibility of creating those dependencies. So the process of creation of a dependency is a separate responsibility often. Here is an example of how we can use service locator. You can see here in what way this is different from what you've seen in the previous lecture. With an IOC container being used in the previous lecture, we resolved objects with their dependencies at the outside boundary. In other words, objects themselves didn't use the IOC container internally to resolve their dependencies. In the case of order processor locator, which is almost the same as a regular DI container, is used within the object. So the main difference between a modern DI container and service locator is in how they are used. Another difference is that service locator is usually a very simple DI container in essence, which doesn't have powerful features like any modern DI container does. Very often, service locator is used as a static bridge to use a DI container in any point of an application, and you'll see that soon. This lecture just describes the service locator design pattern. You'll see the consequences of applying this pattern later in this course when we will talk about the best practices and the anti-patterns related to dependency injection. Here I implemented a simple application which allows to manage the list of students. The solution consists of several projects. The Students Manager is a WPF application which contains views and IOC container bootstrapping. If you want more granularity, you can keep the bootstrapping phase in a separate assembly. MVVM framework is the framework which supports the MVVM pattern and in this case provides a simple IOC container. Let's look at the application more closely. This application supports simple CRUD operations. This is a WPF application and it is implemented with the MVVM pattern. This pattern implies three parts: model, view, and viewModel. Views are represented by XAML files, so views represent the UI. Each view has a corresponding viewModel named accordingly. For example, the main view has the corresponding main viewModel. The UI elements are bound to properties and methods of a corresponding viewModel. This is achieved via a special mechanism in WPF called data binding. For example, if a user clicks Add button on a main view, that call will be handled by the addStudent method, which belongs to the main viewModel. The application is built with the help of a small framework, which I also wrote by myself in order to demonstrate how frameworks provide those themes for plugins. Notice that the main viewModel requires three arguments to be passed via a constructor. The first dependency is the interface, which allows to perform CRUD operations over students. The database in this case is represented by an XML file for the sake of simplicity. Event aggregator allows to pass messages between any components of a system. Again, these details are not very important to our discussion. The last dependency represents a seam provided by the framework. It allows to open and close new views from within view models. When you build an MVVM-based application, you have to connect views and view models somehow. One major way is to instantiate a view and then a view model, and another one is the opposite. At first create a view model and then locate and instantiate a corresponding view. Our framework supports both models. Let's look now at the framework and how our application is getting bootstrapped with this framework. It is the framework who allows to automatically wire up view models, connecting them to views. For providing this feature, a framework has to know which assemblies to scan through, searching for a corresponding view model. The search is based on a naming convention. If a main view was created, then a framework will look for a main view model in the assemblies added to this list by the application which relies on this framework. Here's the chunk of code which scans through assemblies and search for a view model. And now the most relevant part regarding our topic. The bootstrapper base is a big seam which is exposed as an abstract class which has to be implemented in the main of the application which wants to rely on the framework. This seam allows framework to automatically resolve dependencies. For example, create and insert implementers of interfaces. Select assemblies should be overridden by the client. It should return a full list of assemblies which contain dependencies. The getInstance is an abstract method which will be used by the framework to resolve the dependencies, so a client should override this method using an IOC container it wants to use. Configure for runtime and configure for design time should set up the IOC container, and they have to be overridden by a client. The main method of a client should call a start method which sets up the framework. This method sets up all the internal things of a framework. In the end, you also can notice that the method of resolving is assigned to a static public field of the IOC class. This class represents a service locator. With this class, you can request to resolve a dependency from any place you want. This is neat because there is a couple of places in the framework where this method is used. Otherwise, the framework wouldn't have access to the mechanism of dependency resolving provided by a client. Remember that you should call the container only from the infrastructural code. If you explicitly call the IOC in the client's code, you most likely hide the dependencies. Let's look at the client's side. A client inherits from the bootstrapper base. It uses the old and powerful IOC container named Castle Windsor. The Windsor container is defined as a field. The select assemblies returns two assemblies, the assembly of views and view models. The configure runtime instantiates the container. Then it registers the first dependency. By using the Windsor's API, we say that if a container will be requested for resolving the iData provider of student, it should pass the student's XML provider as the implementation of that generic interface. Also, we say that creating the student's XML provider, a container should pass the student's repo.xml string as an argument to the constructor. Event aggregator and iWindow manager are registered afterwards. They are registered the same way, except one detail, which concerns their lifetime. The lifestyle singleton method ensures that the implementers of these interfaces will be created once, and after that, the same instance will be passed everywhere event aggregator or iWindow manager are requested. So they are singletons, and they will live throughout the lifetime of the application until the application's domain is unloaded. In the end, there is a call to the register view models method. look at it. This method adds to the container all the classes whose name ends on viewModal. This is how the architecture with plugins and adapters is implemented. To understand the runtime execution flow, I'll show you the following diagram. The application modal is defined by the WPF framework. WPF defines a startup event. The application subscribes to it, and the handler can be treated as the entry point or the main method. This handler creates the bootstrapper, which inherits from the bootstrapper base defined in our small MVVM framework, and it calls the start method. Start method calls the configure runtime, what leads to the process of setting up the IOC container, the Castle Windsor in our application. WPF provides the point where we set the first view which has to be opened. I just didn't show you. I set it to a special infrastructural view called shell view. This view is a user control which hosts other views. Shell view uses a special auto-wiring mechanism of view models provided by the MVVM framework. Since all the dependencies and all the assemblies are well known for the MVVM framework, it easily locates the shell view model and creates it via the IOC container. Shell view model automatically creates the main view model via IOC, and the corresponding view is created via a special WPF mechanism of data templates. It's okay to use IOC in the shell view model, since this view model is pure infrastructure. It's responsible only for switching the views on top of a shell view. At this point, the application is started, and the main window is visible to the user. Now, when a user clicks on, for example, on the Add Student button, the view model calls the iWindow Manager, which is a part of the MVVM framework, passing to it the type of a view model, the corresponding view of which has to be opened. In case of Add Student, there would be passed the Edit Student view model. And here the framework comes into play. It creates the requested view model via the IOC, then it locates the view type and creates it. After that, it connects view model to a view by setting the data context of the view to the view model's instance. Finally, the framework calls the WPF method show on the window to make it visible. Here's the execution flow. Notice that frameworks provide many ports for the client's code, which sets them by adapters implemented on the client's side. Client code defines the business logic. Framework does its own job by providing all the required infrastructural features. The IOC container takes the responsibility to create dependencies and manage their lifetime. Each part does its own job. Very nice. If you want to change the persistence mechanism, no problem. Just implement the iData provider and set up the IOC as you need, and you're done. No problems. This demo shows how real-world applications may be structured. You can download the source code of this application and study this example on your own. Feel free to debug the application and look how it is built in depth.
Congratulations! You've reached the end of the section. And in this section, you learned that dealing with dependency injection manually is what we call poor man's DI, or pure DI. An IOC container is usually a framework that allows to compose graphs of objects, harnessing super powerful features like managing of lifetime of those dependencies. On the example where we built a trivial IOC container, you've seen that any IOC container is based on reflection heavily. Service Locator is a design pattern that preceded the full-fledged IOC containers. Service Locator, when applied in wrong places of an application, can be considered an anti-pattern. In the next section, you'll learn about anti-patterns that often appear when we design classes. And also you'll learn which refactorings exist that help us to remove anti-patterns.